بسم الله الرحمن الرحيم. اليوم راح نكمل محاضراتنا بخصوص الجنرال ستيبس فور constructing the root locus. احنا في السابق وصلنا للخطوة اللي بتتعلق بالبرانش بوينتس، بس نتيجة للانقطاع اللي صار حاب اعمل كويك ريفيو، مراجعة سريعة على اللي هي خطوات رسم الروت لوكس. أول خطوة من خطوات الرسم كانت عبارة عن determination of the root locus on the real axis، وحكينا في عنا الرول اللي هو الأود نمبر رول، ناقشنا في السابق اللي هي إذا كان if the total number of poles and zeros to the right of the test point is odd then that test point is part of the root locus. Why? Because the angle condition will be satisfied, and if the number of poles and zeros to the right of test point is even then that test point is not part of the root locus. وبالتالي هذا الحكي ناقشناه في السابق. بعدين انتقلنا لموضوع اللي هي البولز والزيروز of the root locus، وحكينا at zeros ال k is equal to infinity و at poles ال k is equal to zero. بناء على الحكي هذا حكينا انه الروت لوكس starts from poles at k equal to zero and ends at zeros at k is equal to infinity. الخطوة الثالثة كانت اللي هي number of branches of the root locus، وحكينا number of branches هي عبارة عن the same number of poles of اللي هي GH اللي هي the degree of the denominator اللي هو اللي عندنا n. وبناء عليه حكينا انه إذا كان عندي ال n is equal to m then all branches start from poles and ends at zeros and there will be no branches that goes to infinity. And if n is greater than m then m branches starts finite branches, they start from poles and it ends at finite zeros, while the remaining n minus m branches they start from poles and go to infinity. We have called or named those branches that goes to infinity, we call them as asymptotes, and those asymptotes they approaches infinity. And in order to identify and describe the asymptotes, we need two pieces of information in order to fully describe them. The first piece of information is related to the angles of the asymptotes, and we have covered that if the number of asymptotes is equal to 1 then there will be one asymptote and its angle will be 180, and if the number of asymptotes are 2 then there will be two asymptotes, one with angle 90 and the other one will be apart from this one with 180 which is equal to minus 90. And if there are three asymptotes the angles will be 60 minus 60 and 180. And if the number of asymptotes is 4 then the initial angle will be 45, and all asymptotes they are distributed equally with 90 degrees. This means that they are 45 minus 45, 135 minus 135. So all of these points they were covered previously, but it's a quick review. And then we covered the second aspect of describing the asymptotes, which is the intersection of those asymptotes on the real axis. All of the asymptotes they will intersect on the real axis at a point called sigma a, and sigma a is equal to summation of all poles minus summation of all zeros divided by n minus m, or summation of all real parts of poles minus summation of all real parts of zeros divided by n minus m. After that we covered the sixth point or sixth step of sketching the root locus regarding the imaginary axis crossing. We said in this regard that we use the most convenient way of determination of the imaginary axis crossing for the root locus, we use the route stability in order to find both K critical and omega critical. We find both of them using the two rules, the no sign change of this first column from one side and the solution of the auxiliary equation above the row of zeros in order to find KCR and omega CR. And we have covered several examples in this regard, and we have reached in our series of lectures till this point. This is the point where we stopped our last lecture. So the seventh step of drawing the root locus is the determination of the what we call the branch points. And branch points, there are two categories of branch points. The first category is called breakaway and the second category is called break-in. Breakaway points, generally they are between poles, and break-in points, they are between zeros. And whether breakaway or break-in, generally if we speak about the branch points, the existence of the branch points, they give us a physical meaning that at this point there is multiple order roots of the characteristic equation. So and then the existence of any branch point means that at this point on the root locus there is a multiple order real roots of the characteristic equation and at this branch point. And as I have said, the branch points, they are categorized as breakaway points and break-in points. Breakaway points, if we have two adjacent poles on the real axis and the segment between them is part of the root locus. And regarding this point, the segment, we have covered it in the first step of the steps of the constructing of the root locus. So again, if there are two adjacent poles and the segment between them is part of the root locus, then there must be a breakaway point. And the second category of branch points is the break-in points, and this break-in points happens if we have two adjacent zeros, and also the segment between those two adjacent zeros, they are part of the root locus. This means that there must be a break-in point. And if we can describe this, I will describe it using this sketch. Assume that we have here two real poles and here two real zeros. This means that the root locus will start from this pole. The root locus will start from this pole and also will start from this pole, and after that they will meet a certain point and then they will depart. And finally we know that the root locus, since we have two poles and two zeros, this means that there are no asymptotes that are approaching infinity. We know that there should be one root locus or one branch of the root locus that will end with this zero and the other will end with the other zero. This means that the two branches, they will meet each other at this point, and then one will go to the left hand side and one will go to the right hand side. This means that this is a break away point and this is a break in point, and as we have said, this is a breakaway because it's between two adjacent poles, and the segment between those two adjacent poles is part of the root locus, and here this is a break endpoint because it's between two adjacent zeros, and the segment between the two zeros is part of the root locus. So this is what's meant by break in and break away points in this regard. So branch points, characteristics of the branch points. Number one is they lie on the real axis. And the second characteristic is that at the branch points still we are satisfying the characteristic equation, which is 1 plus GH or 1 plus Kn over D is equal to 0. Okay, so we have understood that the branch points correspond to multiple order roots of the characteristic equation, and they are classified as break-in or break-away points. So this is from physical meaning, but we need to know the procedure how to solve or how to find the branch points. So the procedure is, we know that we have covered it previously, that K is equal to minus D over N. We have covered this. K is equal to minus D over N. And based on that, we should, the first step of the solution process is to derive this equation and find dk over ds, derive it with respect to s, which is derive this equation with respect to us, and we should solve it only for real roots because branch points, they only exist on real axis. And so if we have any complex roots or imaginary roots, they are discarded and they are neglected. They are don't care condition, we don't pay attention to them. The only roots that we take into consideration are the real roots of this equation dk over ds. And after determination of the real roots, if the real roots, they are part of the root locus, then they are really branch points. But if they are not part of the root locus, then they are not branch points. So for all of the roots that are roots of this equation, the real roots are, in the first phase we find the real roots, and from the set of real roots, only the real roots that are part of the root locus, they are branch points. Any other roots, they are not branch points if they don't exist on the real axis segments of the root locus. So and they should exist between poles, adjacent poles, or zeros. There is one important information about the characteristics of the branch points. The branch points also can be described in terms of their angle, departure angle of the real axis, okay, and the angle between all of the branch points. And this point, the calculation of the angle, initial angle or angle of departure from the real axis, and the angles between all branches that will meet, it's similar to what we have done in the asymptotes, the angle that we called phi a. So the initial angle is found by divided 180 over n, and n is the number of branches that will meet or depart or arrive at this branch point, and normally in most of the cases n is equal to 2. So if n is equal to 2, this means that the initial angle will be 90 degrees, and the branch points, this is the second point, the branch points, they are equally spaced. The tangent to the loci at the branch points, they are equally spaced over 360. This means that if n is equal to 2, they will be separated by 180 degrees. If n is equal to 4, they will be separated by an angle of 90 degrees. So this is exactly similar to what we have described before, and this is what I mean by the angles here. The angle will be plus 90 minus 90, and here also the angle will be plus 90 minus 90. Why? Because we have two branches, they are meeting each other, okay, at this branch point. So one will go up with plus 90 and the other will go down with minus 90, and also here one will go down and one will go up, and the initial angle in both cases will be 90 degrees and the other angle will be minus 90 degrees. So this is what I mean in the angles of departure from the real axis and the displacement of the tangents to the loci at the branch, at the breakaway points or break-in points. After that, we will switch to the eighth point or eighth step of the root locus construction, which is related to the angle of departure of a complex pole or angle of arrival theta d, or angle of arrival to a complex zero, which is theta a. So here departure theta d and arrival theta a. And why we called departure for a complex pole and arrival to a complex zero? Because as we know that root locus starts from the poles as a matter, based on this, then it should depart, while root locus ends at zeros as based on that it should arrive to the zero. So regarding the calculation of angle of departure or angle of arrival, theta d or theta a, they are simply calculated using the angle condition, where the net angle condition of all other poles and zeros are equal to odd multiples of 180, and this is we have completely described in our previous lecture. The angle condition, the summation of all angles of the zeros minus the summation of all angles of the zeros should be odd multiples of 180 degrees. So how to define or how to determine the angle of departure or angle of arrival? We should know that if we have and let me describe it in the following manner. If we have this complex pole, okay, and if we have other zeros or poles on the real axis, and there should be this complex pole conjugate with negative j. Okay, so we are interested in the angle of departure of this complex pole. So what is meant by angle of departure? When the root locus will start from this branch, will it move, depart by this angle, this angle, this angle, this angle? What's the angle that the initial angle of departure from this complex pole? So this is what's meant by the angle of departure. And in order to find this angle of departure, okay, we assume a test point. We assume a test point in the very close neighborhood of this concerned So if we assume that this is the test point, which is in the very close neighborhood to the complex pole. This means that when we want to apply the angle condition, from all other poles or zeros, okay, when we find the angle, the concerned angle from all other poles and zeros, then we can see the test point, this test point, and the concerned pole will be at the same location if we look at them from all other poles and zeros. So this means that the angle of the test point and the angle of the corresponding pole will be the same. Okay, so this is one important fact that should be understood in this stage. And regarding the angle of departure from the complex pole, as I have said, we assume that it's in the very neighborhood. Then this means that this is the test point and this is the pole or the pole of interest. We calculate the angle in the normal manner that we have learned before, that it will be from the pole or zero of interest to the test point. This means that this will be the angle. Okay, so the angle will be this angle from the pole or zero of interest to the test point, and we can measure it in the counterclockwise from the positive real axis. So this is the angle that we will calculate. So after this discussion, we can find the angle of departure and the angle of arrival from complex poles or zeros. Regarding the angle of departure, this means that theta d, okay, will be calculated as 180 odd multiple minus the summation of all angles from all other poles plus the summation of all angles from all other zeros, while the arrival angle will be calculated in a similar manner. Okay, so theta A will be the odd multiples of 180 minus all of the angles from other zeros plus all the angles from poles of GH. So here we will cover them in words here, as it's obvious. Theta D or theta A, what is it? It's the difference between the net angle except that pole or zero of interest, whether we are calculating theta D or theta A, due to all other poles or zeros and odd multiples of 180. So for theta D, it's equal to 180 minus sum of all vectors to the complex pole in a question from other poles plus the sum of all vectors to the complex pole from all zeros. So here we have said all zeros, but we have said other poles because we are calculating it theta for certain one of the poles. So this is why we said here other poles. This is why we said here it's calculated from other poles, because we are calculating at certain pole, while regarding the zeros we calculated from all other zeros. Similarly, if we will describe the angle of arrival. What's theta A? Theta A is 180 minus sum of angles of all vectors to the complex zero in equation from, look here, from other zeros, because we are calculating it at one of the zeros, plus the sum of all vectors to the complex zero in equation to all, not other, to all poles. And in this way we find the angle of departure and angle of arrival for the concerned pole or concerned zero of the GH transfer function, loop transfer function. And finally, we end up with a reality or a nature of the root locus, that root locus is symmetric about the real axis. So, and the symmetry axis is the real axis. What is above the real axis should be symmetrical with anything below the real axis. So in this manner we have completed the steps of constructing the root locus, and now we will switch to some important notes that I will cover in order to understand the complete information about the root locus. The first note is related to the fact that if the root locus has asymptotes greater than unity, and the number of asymptotes is n minus m, so this means that n minus m is greater than unity. This means that, and I have covered this previously in my previous lectures, this means that there will be asymptotic angles that start with 90 minus 90 if n minus m is equal to 2, or if n minus m is equal to 3, there will be 60 minus 60, 180, and so on. So since the angles, they are directed to the complex domain, this means that it's always possible to select a pair of complex conjugate poles that satisfy certain damping ratio or certain undamped natural frequency. If we are interested in certain damping ratio, we will find the intersection between the root locus and the beams, as we will cover later, with angle of theta, which is equal to cosine inverse of zeta from the negative real axis. And after that, the intersection point, it's called P1 and P1 conjugate. These are the points that satisfy certain damping ratio, and we can find the value of K after applying the magnitude condition, which is equal to K magnitude is equal to D over N. Okay, and this is the normal way of designing control systems using root locus, and we will cover this in details in the next chapter. The second point states that root locus branch may be on one side of the asymptote or may be on the other side of the asymptote. This means that if the root locus has n minus m greater than 1, okay, and generally greater than 2, this means that the asymptote might be above the actual branch of the root locus or might be below the actual root locus branch. Okay, so in order to clarify things, assume that we have this system, first pole, second pole, and third pole. For this system, we know that n minus m is equal to 3, and based on that we have 3 asymptotes with angles of 60, minus 60, and 180. These are the asymptotes. These are the asymptotes, not the branches of the root locus. Okay, and if we will draw roughly the root locus randomly, but not exactly, then the root locus might behave in this, then the root locus might behave in this manner, and in this way the root locus, the actual branch of the root locus, is below the asymptote, or might be in this manner. Okay, and in this way, in the second scenario, the root locus, the actual branch of the root locus, will be above the asymptote. So this is what I meant by it might be on one side of the corresponding asymptote, or might cross the asymptote and go to the other side. The third point in our lecture, okay, is related to the branch points, which are breakaway and break-in points. And as I have said, they only lie on real axis. And if there are two adjacent poles on real axis, okay, and the segment is between them is part of the root locus, then at least there must be breakaway point. And if there are two adjacent zeros on the real axis and the segment between them is part of the root locus, then there must be at least break-in point between those two zeros. After that, we will cover some important information about the imaginary axis crossing. Imaginary axis crossing. This point I have already covered previously. Okay, the imaginary axis crossing, it can be found using one of two alternatives. The first alternative that we have already covered is the Routh stability, and from this Routh stability we can find K critical and omega critical. The other scenario is by letting S is equal to J omega. Why? Because if at the imaginary axis, if we place the test point at the imaginary axis, this means that the real part is 0. And based on that, S will be only equal to J omega. So if we substitute this S is equal to J omega in the characteristic equation, okay, we will get two equations. One equation regarding the real part and the other equation regarding the imaginary part. And both of them should be equated to 0. This means that we have two equations equated to 0, and we have two unknowns. What are the two unknowns? They are K critical and omega critical. But those two equations, they will be nonlinear. And based on that, there will be a difficulty in solving them depending on the order of the characteristic equation. And this is why we most of the time using the Routh stability, and we rarely use this approach by substituting S is equal to J omega in the characteristic equation. And regarding the next comment, the magnetic condition, any test point on the root locus, and it should be on the root locus, the value of K for that test point, it's found by the product of all lengths between that test point and poles divided by the product of all lengths of that test point to the zeros. And one important note in this regard, which shows the sensitivity of the root locus to certain configurations, is that in some cases, and it's rarely happen, that in a slight modification in the pole 0 configuration might change or might produce significant changes in the root locus drawing. So if we pay attention to this figure and this figure, the relative locations of the poles and zeros of GH, in both of them, they are very close to each other, but look, the behavior of this figure is different from the behavior of this root locus. And the exact numbers if we need to go to the details and show the exact numbers, we assume that G1 is equal to this. So, and G2 is equal to this transfer function. The only difference between G1 and G2, if you pay attention, is the simple zero here, the real zero. It was here 6, while it's here 6.5. This is the only difference, while the poles of G1 and G2, they are the same. The poles of G1 and G2, they are the same. So the 0 in the first example is located at -6, while the 0 in the second example, G2, is at -6.5. And if we draw the root locus, this is the figure of root locus for G1. Okay, while if we proceed, this is the root locus. This is the root locus for G2. So if we compare both of the figures, there is a significant change in the drawing of the root locus between both of them, but this happens rarely, and in rare cases. It's not the most common phenomena in drawing of a root locus. After that, we jump to the next comment, which is related to writing the root locus in this format. The characteristic equation, writing the characteristic equation in this format, 1 plus k n over d is equal to 0. It's called Evans root locus form. So it's important to write the characteristic equation if the characteristic equation is given to you as a polynomial, and it's not given directly in this format. Then the designer should convert the characteristic equation from the polynomial format to Evans root locus format. And how this happens, I will cover it with like a simple example. If we consider that s to the power 3 plus k s to the power 2 plus 10s plus 5k is equal to 0. Okay, so this means that this is the characteristic equation in polynomial format. So we should rewrite it such that it should be in this format. And in order to proceed and write it in this format, we should collect the terms containing k in one side and the terms not containing k in other side. So this means we should rewrite k, or the terms not containing k, as s to the power 3 plus 10s. These are the terms non-containing k. Okay, and then after that we will continue plus k multiplied by s squared plus 5. Okay, and all of this should be equal to 0. So after distributing or rewriting, the characteristic equation, or splitting the characteristic equation into two terms, the first term is the one containing k, and the second term is the one non-containing k. Then we divide after that the characteristic equation by the terms non-containing k. So we divide it by this, and after the division we will get 1 plus kn over d. This means that this will be the d, and this will be the polynomial of n. This be d and this will be n, and in this way we have converted our polynomial from the standard polynomial format to the Evans root locus form. Okay, and after that there's another form that we should express the characteristic equation in it, which is the factored form. This is the Evans root locus form, and after that we factorize the polynomial n of s to this and the polynomial d of s to this format, and in this way this equation will be ready for handling and drawing the root locus in this way. Okay, the next note, if there are no poles or zeros on the real axis, then there will be no components, no real axis components that are part of the root locus. And this is true because the number of total number of poles and zeros, okay, to the right hand side of any test point will be always even, and since it will be always even, this means that there will be no real axis segments that are part of the root locus. Okay, after that, if there is no asymptotes, this means that n minus m is equal to 0, or n is equal to m. What does this mean? This means that the number of poles is equal to the number of zeros, and all of the branches of the root locus, they are finite. Okay, and asymptotes, as I have said previously, they are symmetric about the real axis, and this is, we have capitalized on this note while calculating the angle of the asymptotes phi a, and this is how to find the sigma a, which already we have covered. And branch points take place when two or more loci or branches of the root locus, they join and then diverge. I am only covering the bolded notes. Any other notes, they have been previously covered and they should be understood due to the previous discussion and coverage. And the next note, single poles or zeros on the real axis, they have angle of departure and or arrival of 0 or 180 degrees. And the point where the root locus intersect the imaginary axis crossing, at this point exactly, the imaginary axis, the system will be marginally stable. And the next note, not every root locus will have imaginary axis crossing if the poles and zeros of the root locus are all in the left half side of the S-plane, and the n minus m, the number of asymptotes, is less than or equal to 2, then in most cases there will be no imaginary axis crossing in this case. The root locus will definitely cross the imaginary axis if there are more than 2 asymptotes, and this is true based on the angles of the asymptotes. And if we have n minus m is equal to 1, the angle is 180 degrees and the asymptote is directed in the left half side. If n minus m is equal to 2, the asymptotes they are minus 90, and still we are in the left hand side. And if the number of asymptotes is greater than 2, this means that the asymptotes will be the angles of the asymptotes will be 60, minus 60, 180 if n minus m is equal to 3, and if n minus m is equal to 4, the initial angle will be 45. And for any initial angle that is less than 90 degrees, this means that there must be a value of k beyond which the root locus will cross the imaginary axis and your system will become unstable. And there is a good chance that the root locus may cross the imaginary axis if there are poles or zeros close to the imaginary axis and the angle of arrival or departure, they are directed toward the imaginary axis. So in this way we have covered the majority of the most important notes that they were not covered previously, and now we will summarize the 7 steps of sketching any root locus. In the first step we will prepare the root locus sketch, and in this way we should write the characteristic equation as I have said in the Evans root locus form, and this is the Evans root locus form: 1 plus kn over d is equal to 0. And then we should factorize the numerator and denominator polynomials into m zeros and n poles, and after that we should locate the poles and zeros of GH in the S-plane, and we give the symbols of small zeros or O's to the zeros and X to the poles, and we know that root locus start from poles and ends at zeros, and the determination of the number of branches or the number of separate loci, the number of branches or the number of separate root loci, they are n, which is the degree of the denominator, and n is the number of poles and m is the number of zeros. After that, it's an important fact that the root locus is symmetrical about the real axis, and we locate in the second step. All of these we are still in the first step. Now we will switch to the second step of drawing the root locus. The root locus, we should locate the segments of the real axis that are part of the root locus, and we should use the odd number rule as I have previously covered. After that, the asymptotes that approaches infinity, they have sigma A intersection point and phi A angles, and sigma A is calculated as I have previously covered, summation of all poles minus summation of all zeros divided by n minus m, and phi A is calculated by 180, the first angle 180 divided by n minus m, and the remaining angles they are equally distributed over 360, which is equal 360 divided by n minus m. And in the next step we should determine the imaginary axis crossing if the root locus will cross, and we have covered two approaches. One of them is using the route stability, and the other, which is more complicated and it's not preferable for us, by substituting or letting s is equal to j omega. After that we determine the branch points if does exist by letting k is equal to d over n, and then we derive it and equate it to 0, and we determine the roots that are real, and within the real roots we only select those roots that are part of the root locus, and they should be break-in or breakaway points, and if there are two adjacent poles and the segment between them is part of the root locus, then it's a breakaway point, and if there are two adjacent zeros and the segment between them is part of the root locus, then there must be a break-in point. And in the final final step before sketching complete the root locus sketch, the angle of departure from a complex pole and the angle of departure from angle of arrival to a complex zero, they are based on the angle condition as I have previously covered, and after the determination of all of the previous steps from 1 to 6, then we can complete the root locus sketch in this manner. So these are some rough root locus sketches that I will just cover some of them. I will cover this one because in this one here we have this break away point, and the number of branches that are met at this branch point, breakaway point, is 4. So based on the calculations of the angle, our initial angle will be 45 for the one of the angle of departure from the real axis, and the remaining should be equally distributed over 360. This means that 360 divided by 4, and this gives 90 degrees, and this is why this is 90 degrees, 90 degrees, 90 degrees, 90 degrees, and this initial angle is 45, which is equal to 180 divided by 4. Why we have divided by 4? Because we have 4 branches. They are met at this point, they meet at this point, and after that they depart. Okay, and the other figure that I will discuss is this figure. In this figure, as we see here, there is here a breakaway point, because we have 2 adjacent poles and the segment between them is part of the root locus, and the root locus should depart this point with 90 degrees, minus 90 degrees angles, and it should arrive to this point, which is the break-in point between 2 adjacent zeros. And if we have 2 adjacent zeros and the segment between them is part of the root locus, then there must be a break-in point. In this manner, I have covered all of the steps regarding the drawing or the sketch of the root locus, and I will finish my lecture here, and in the next lecture I will cover the example. Thank you.